In 1991, a Japanese physicist, Sumio Ijima, conducted a momentous experiment. An experiment that introduced the world to a material so strong that it could revolutionize how engineers approached design. Taking two graphite rods as electrodes, Sumio applied a current across the rods. A spark arched between them, and with it, a cloud of carbon gas puffed into existence, vaporizing the tip of the anode rod. As the carbon-laden air settled on the chamber walls, it formed a thin layer of black soot. Within it, a strange new material appeared, tiny, single-layer straws of carbon. Sumio Ijima had just created carbon nanotubes. Laboratory testing of these mysterious little tubes in the following years would reveal that these nanometer-wide, hexagonal lattices of carbon had the strongest tensile strength known to man. And this was just one of many incredible material properties they displayed. Carbon nanotubes are light, conductive, and biocompatible. It soon became clear that the carbon nanotubes had the potential to be the building blocks of futuristic new technologies, the most efficient computers, transformative medical devices, synthetic muscles, or perhaps the most ambitious of all, space elevators, the dream of countless sci-fi authors. Carbon nanotubes have promised to be the catalyst for the next revolution in technology. But putting this revolutionary material to work will not be easy. It turns out that building a fiber that is actually a single molecule of any significant length is incredibly difficult. To understand this fascinating molecule, let's dive into the chemical makeup of carbon nanotubes. Carbon is a very familiar element. It's in everything we eat, sleep on, and step over. It is the element that holds our DNA together. It forms the carbohydrates, proteins, and lipids that we depend on to build and fuel our bodies. It's the basis of life as we know it. Its ubiquity in our lives is a result of its versatility. Its chemical properties allow it to take many different shapes, each impacting its material properties in diverse and unique ways. To understand this, we need to understand the basic models of how we visualize how electrons orbit around the nucleus of an atom. To start, we have the simplified Bohr model, which separates the electrons into shells. The first shell can contain 2 electrons, while the second shell can hold 8. An atom wants to fill each shell to be stable. Let's take an atom of carbon which has 6 electrons to see how this plays out. First, we fill the first shell with its 2 electrons. Then we have 4 electrons left to fill the next shell, leaving 4 open positions in its outer shell. The 4 open positions mean that carbon willingly interacts with many other elements as well as itself, often by sharing electrons in a special type of bond called a covalent bond. This versatility allows carbon to create many different kinds of molecules. Take hydrocarbons. Hydrogen has 1 electron and seeks 1 electron to fill its inner shell. So, carbon likes to form 4 covalent bonds with 4 hydrogen atoms to form a stable 8-electron outer shell, while helping hydrogen form a stable 2-electron shell. This is methane, an incredibly common molecule that is the main ingredient in natural gas fuels. This is just one arrangement carbon can take. Hydrocarbons take a huge range of shapes and configurations, but what we are interested in is how carbon bonds to itself. But this simplified Bohr model doesn't give us an understanding of how carbon-to-carbon bonds take radically different shapes. We need to dive a little deeper before we can understand the magic of carbon nanotubes. Electrons don't travel in neat 2D circular orbits as the Bohr model would suggest. In fact, we can't even know the position and speed of an electron. Instead, we can make predictions about electrons' general locations in 3D space. We call these orbitals, and they are regions where we have about a 90% certainty that an electron is located somewhere within that region. This can get pretty complicated, but for now, we just need to concern ourselves with 2 types, s and p orbitals. S orbitals are spherical in shape, with the nucleus of the atom at their center. P orbitals are often called dumbbell-shaped, but I don't know what gym these nerds are going to because I have never seen a dumbbell like this. It's more of a figure of 8 shape like the infinity symbol. In the ground state, electrons will occupy the lowest energy orbitals first, which in this case is the 1s orbital. It can hold 2 electrons. Next, we have the 2s orbital, which has a larger sphere and can also hold 2 electrons. Then we have our 3 p orbitals, one aligned along the x, y, and z axis, each capable of holding 2 electrons. Carbon in its ground state has the 1s and 2s orbitals filled with 1 electron in the px orbital and 1 in the py orbital. To be stable, carbon wants to fill these 3 orbitals with 2 electrons each. Now this is where things get a little funky and confusing, and yes, it will be on your final exam. Carbon can bond to itself in different ways that affect these orbital shapes. Take diamonds. To fill these orbitals, carbon bonds with 4 neighboring carbon atoms. To do this, it promotes 1 electron from its 2s orbital into the empty pz orbital. This pz orbital is higher energy than the 2s one, and the electron doesn't want to stay there. So the carbon atom takes a new hybrid orbital shape to compensate. This is called sp3 hybridization, which is a mixture of s and p orbital shapes and looks something like this, where one side of the figure of 8 expands while the other contracts. The 2s and 3p orbitals are transformed into these new sp3 orbital shapes. They repel each other equally in this 3D space to form this 4-lobed tetrahedral shape with 109.5 degrees between each lobe. Covalent bonds now form between the carbon molecules where these orbital lobes overlap head-on in what's called a sigma bond. This creates a repeating structure like this, and it's this rigid framework of carbon atoms that makes diamond extremely hard. Now, what's fascinating to me is that you can take the same carbon atoms and now form graphite, a material so soft that we use it as pencil lead and as a lubricant. How does that work? Here, a different hybridization occurs. Once again, 1 electron from the 2s orbital is promoted into the pz orbital. But this time, the s orbital hybridizes with only 2 of the p orbitals, giving us the new sp2 hybridization. This gives us 3 sp hybrid orbitals and 1 regular p orbital. This new arrangement causes the orbitals to take a new shape, with the 3 sp orbitals arranging themselves in a flat plane separated by 120 degrees, with the non-hybridized p orbital perpendicular to them. Now, when the carbon atoms combine, the heads of the sp orbitals overlap once again to form this flat hexagonal shape. A hexagon pattern is naturally a very strong and energy efficient shape. For example, bees don't intentionally build honeycombs in hexagons. They form as a result of the warm bee bodies melting the wax, and then the triple junction hardens in the strongest formation. The shape is frequently used in aerospace applications where high strength and low weight is a priority. These sp2 bonds are stronger than sp3 bonds because they have a higher s character. This sounds complicated, but all it means is that they are more like s orbitals than p orbitals. Because there are 3 sp2 bonds, they have a 33% s character, whereas sp3 orbitals have 4 sp bonds, giving them 25% s character. S orbitals are closer to the nucleus, making sp2 bonds shorter and more electronegative than sp3 bonds, and thus stronger. This hexagonal structure and strong bonds makes graphene exceedingly strong. Laboratory testing of graphene using atomic force microscopes has shown graphene has a Young's modulus of 0.5 terapascals and an ultimate tensile strength of 130 gigapascals. So strong that if we could somehow create a perfect sheet of graphene, which we can't, we could build an invisible, single atom deep hammock that could support the weight of a cat. Imagine the amount of cats we could confuse. That's the world I want to live in. That's an entertaining but not terribly useful application. But graphene is a very common material, and the form we are used to, graphite, is not strong. This hexagonal shape itself is extremely strong, But because graphite forms single atom layer sheets with only weak van der Waal forces holding them together, the sheets can easily slide over each other, which is the reason graphite is so soft. Now, what is interesting is that carbon nanotubes take the same repeating hexagonal structure as graphite. The ends of the sheets are simply looped and connected together to form a tube, and this structure is what gives carbon nanotubes their incredible strength. Researchers found that single-walled nanotubes have similar strength to that of graphite, about 130 gigapascals. For non-engineers in the crowd, let me rephrase that. It's a lot, about 100 times greater than that of steel, and to boot, it's vastly lighter. If this material could be feasibly manufactured into a single, extremely long fiber, it could potentially open up entirely new design possibilities, like the space elevator. I'd explain exactly why carbon fibers would make space elevators possible now, but I already did that in a past video that I will link at the end of this one. So, where are these space elevators? Things have changed a bit since the days of Sumio Ijima's first discovery. The most promising method of industrial scale production of high purity carbon nanotubes is chemical vapor disposition. In this manufacturing method, a precursor gas containing carbon, like methane, is introduced into a vacuum chamber and heated. As the heat increases inside the chamber, the bonds between the carbon and hydrogen atoms begin to decompose. The carbon then diffuses into a melted metal catalyst substrate. This then becomes a metal-carbon solution, which eventually becomes supersaturated with carbon. At this point, the carbon starts to precipitate out and form carbon nanotubes, while the hydrogen byproduct is vented out of the chamber to avoid an explosion. Our research has focused on increasing the length of these nanotubes while not sacrificing their structure, yield, or quantity. While some labs have gotten individual tubes as long as 50 centimeters, it's been a struggle to get larger bundles of tubes, which are called forests, to a length greater than 2 centimeters. This is because the catalyst is guaranteed to deactivate at some point during the growth process, terminating the growth of the nanotube. The key to growing longer nanotubes is minimizing the probability of the catalyst deactivating. In 2020, a research team based in Japan managed to grow a forest over 15 centimeters in length, 7 times longer than anyone else, using a new method of chemical vapor disposition that managed to keep the catalyst active for 26 hours. They did this by adding a layer of gadolinium to a conventional iron aluminium oxide catalyst coated on a silicon substrate. Then, using a lower chamber temperature, small concentrations of iron and aluminium vapor were added into the chamber. These factors combined managed to keep the iron aluminium oxide catalyst active for much longer. This method is a major leap forward that could allow carbon nanotube products to begin entering the market. But we are still a long way from a space elevator. Most products today call for the fibers to be woven together to form a yarn-like textile. One study I found wove together 1 mm long nanotubes into a yarn and then impregnated that with an epoxy resin to form a composite material, which had a pretty good tensile strength of 1.6 gigapascals, beating aluminium in its strength to weight capabilities, but below that of traditional carbon fiber composites. However, these new longer nanotubes may give us stronger woven fibers in future. It's important to remember that carbon nanotubes aren't just strong. Their most exciting near-term applications will come about as a result of their other material properties, like their conductive abilities. Like graphite, nanotubes are highly conductive, because each carbon atom is only bonded to 3 other carbon atoms. So, each atom has 1 free valence electron available for electrical conduction, making carbon nanotubes excellent conductors. The conducting core of cables that make up our overhead grid lines are typically made from aluminium, even though aluminium is a poorer conductor than copper, and thus causes a greater loss in power over the lines. It's used because it's cheaper and lighter, allowing support structures for overhead lines to be spaced further apart. Individual nanotubes are orders of magnitude more conductive than copper, but creating a yarn of nanotubes that could match copper has been a challenge. Electrons move through individual nanotubes very efficiently, But when the tube comes to an end, the current meets resistance when jumping to a neighbouring tube. So these longer tubes developed last year are opening doors to conductors that are vastly lighter than aluminium and more conductive than copper. These could be used for grid connections, allowing our power lines to stretch further without supports and minimize the loss of power to heat resistance. But for now, the price of nanotubes likely shuts that door. Instead, we could see these wires being used in super lightweight aircraft or cars. They are even being investigated as a means of helping composite structure planes like the 787 survive lightning strikes. The 787 is primarily composed of carbon and glass fiber reinforced plastics, but because they do not conduct electricity, the plane has additional conductive structures added to protect it from lightning strikes, like a thin copper mesh. This mesh adds weight that increases fuel consumption. This could be drastically reduced by including a carbon nanotube mesh on the surface of the composite instead. Nanotubes are also quite elastic, capable of stretching to 18% of their original length and returning to their original shape after. This could allow conductive carbon fiber wires to be incorporated into wearable technology. Perhaps the most exciting application is biomedical devices. Carbon nanotubes are biocompatible, meaning they are not toxic, non-reactive, and do not elicit an immune response. Combine this with their conductivity, flexibility, and strength, and nanotubes become extremely attractive as neural interface material. A large part of Neuralink, Elon Musk's neural interface company's efforts have been focusing on creating smaller wires and the machines needed to implant them. Larger, stiffer wires tear into flexible brain tissue over time and causes scar tissue to form around the wire, preventing signals from passing from the neurons to the wires. Nanotube wiring could be made smaller and more flexible while being accepted by the body, a potentially game-changing material for biomedical implants. As with every major material innovation, from age-hardened aluminium ushering in a new age of aviation, to silicon semiconductors opening up an entire new world for computers, carbon nanotubes have the potential to open the door to design possibilities and technologies we have yet to imagine. New materials radically change how and what we build, and learning about manufacturing processes for complex machines really gives you an insight on how a material like this could change things.